Section 3.7, Rational Functions. In this section, you will learn to use an arrow notation, find the domains of rational functions, and identify vertical and horizontal asymptotes. Let's start with the rational functions. Any function which has a polynomial on top and the bottom of a fraction is called a rational function. Example number 1, which of the following are rational functions? So don't forget a polynomial on top and bottom. So the first one, f of x equal to x plus 3 over x squared minus 9. Look at the numerator and the denominator. Those are polynomials. So this is a rational function. Next one, g of x equal to 3 over x plus 6. Yes, this is also a rational function. How about h of x? The top is x minus 1. The bottom is 2 raised to x plus x squared minus 4. So this is not a rational function. Why? Because we have this 2 raised to x. Because 2 raised to x is not a polynomial. Okay. Next is using an arrow notation. Since rational functions will usually have domain issues, we need to develop some notation to indicate what happens as we approach the restrictions on the domain. Let's take the next example as a starting point. Example number 2, express the behavior of f of x is equal to 1 over x as it approaches the restriction of its domain using an arrow notation. So this is the graph of 1 over x. So what do you see here? So if you take a look at these graph here, from the left, if you follow this graph from the left, you see the arrowhead here, meaning it's approaching negative infinity. So we can say that as x approaches 0 from the left, the minus here is from the left, this is 0. As you can see that this graph here from the left is not touching this x equals 0. So let's say 0 from the left, which means these graph here, as x approaches 0 from the left, we can say that our f of x approaches negative infinity because this goes down. And from the right, so let's have this from the right. If we follow this graph, it goes up. So we can say that as x approaches 0 from the right, so we use plus, f of x approaches, if you follow this green graph, approaches positive infinity. Okay. And in general, arrow notation has the following meanings. Notice that we already used the arrow notation when we discussed the end behavior. So follow the end behavior here. So like what I said again, from the left, if you follow this graph here, the end behavior of this, it is orange, it goes down, and that is approaching, f of x is approaching negative infinity. That is as x approaches 0 from the left. From the right is this green graph here. As x approaches 0 from the right, f of x approaches positive infinity because it goes up. So that's what you mean by as x approaches a from the left, from the right, x approaches infinity, that is to the right is positive infinity, to the left is negative infinity. Okay, so I want you to go check your OpenStax book for these arrow notations. Okay, let's have another example here. Use arrow notation to describe the end behavior and local behavior of the function graph below. So what do you notice about this graph here? So again, we can have our left end behavior and right end behavior. So you can say that as x approaches negative infinity, this one here, if you follow this as x approaches negative infinity, is approaching what value of f of x, or what value of y? That is approaching 4. And how about our right end behavior? So this is the right end behavior. It's approaching, as x approaching positive infinity, your f of x approaches also positive 4. Okay, so take note of these two end behaviors. Next, asymptotes. In the last example, we found a vertical line and a horizontal line that the graph couldn't cross. You see these dotted lines here? So this is what you, this is what you call the vertical asymptote. And this is horizontal. So we call these boundary lines, those dotted lines, as asymptotes. So we have the vertical asymptote and the horizontal asymptote. So an example here, find the horizontal and vertical asymptote of the function graph below. This dotted line here, that is your vertical asymptote. That is when x is equal to -2. And this green here, that is your horizontal asymptote. That is when y is equal to 3. Okay, and we can see here that also as x approaches, you see here you're at -2. Let's say -2 from the left. We can say that f of x goes down, approaches negative infinity. How about as x approaches -2 from the right? This graph here goes up. So f of x approaches positive infinity. Okay, next is find the domains of rational functions. Since the rational functions have denominators, we must set denominator equal to 0 to find the domains. So again, take note of that. We must set denominator equal to 0 to find the domains. Let's say, for example, f of x equal to x plus 3 over x squared minus 9. We know that x squared minus 9 is factorable, and the factors are x plus 3 and x minus 3. So we can cancel out the x plus 3's. So this is, and simplified, is 1 over x minus 3. So remember, set the denominator equal to 0. Your denominator is x squared minus 9, and we know that the factors are x plus 3, x minus 3. So if you set that to 0, so x plus 3 times x minus 3 is equal to 0. So we can say that x plus 3 is equal to 0 and x minus 3 is equal to 0. So x is equal to -3 and x is equal to 3. So we can use this to write our domain. So that's what we want. Find the domain. So the domain is from negative infinity to negative 3, union from negative 3 to positive 3, union from positive 3 to positive infinity. So this is the answer. So let's take a look at the graphical view of that given function. If you want, you can type this. If you have a graphing calculator or just Desmos, I use that a lot. You can just type as is x plus 3 over x squared minus 9. You will see this graph. Look at the restrictions here. These are our two restrictions. X equals negative 3 and x is equal to 3. So look at that. At x is equal to 3, that is your vertical asymptote. And that is your denominator. And what do you see here? When x is equal to negative 3, there is an open dot, or we call this as a hole. Meaning, take note of this, when you cancel out a numerator and a denominator, that makes it a hole. Okay, so those are the restrictions when x is equal to negative 3 and x is equal to 3, and we use that to write our domain. So take a look at this graph. The graph is from negative infinity to negative 3 because there is no point at negative 3, and then it's continuous from negative 3 to positive 3, and then there is a break here again because you have a vertical asymptote, and then from 3 up to positive infinity. Okay, so this hole here, we call that open dot as a removable discontinuity. Discontinuity. Okay. All right. Let's have another example here. Find the domain of f of x equals x minus 2 over x squared minus 4. And again, x squared minus 4 here is factorable. So x minus 2 over factors of it are x plus 2 and x minus 2. Cancel out the x minus 2's. So this is equal to 1 over x plus 2. So with this is your denominator. You start with this, meaning that is your vertical asymptote. When you set this to 0, it's going to be x equals negative 2. And also, we canceled out the x minus 2's, meaning that is a hole or the removable discontinuity. That is when x is equal to negative 2. Removable, or we call it a hole. There is a hole at negative 2. So how do we write our domain? So if you want to write the restrictions, that's going to be those two. The vertical asymptote and a removable discontinuity, x is equal to positive 2. Sorry, this should be positive 2. Okay, so now how do we write our domain? So from left to right, from negative infinity to negative 2, union from negative 2 to 2, union from 2 to positive infinity. So this is our domain. Okay. Next page. Identifying horizontal and slant asymptotes. So take note of all this. We find the horizontal asymptote of a rational function by looking at the degrees of the top and the bottom. Degrees. Okay, so if the degree of the top is less than the degree of the bottom, the horizontal asymptote is at y equals 0. Okay, if the degree of the top is equal to the degree of the bottom, the horizontal asymptote is at the ratio of the coefficients. And if the degree of the top is +1 degree of the bottom by 1, we call this as a slant asymptote. Again, if the degree of the top is greater than the degree of the bottom by 1, meaning we have a slant asymptote, and since we have a slant asymptote, meaning there is no horizontal asymptote. Okay, so visually, that means, take a look at these graphs here. So look at this first graph here. Do you have a horizontal asymptote when y is equal to 0, meaning the degree of the top is less than the degree of the bottom. That is when you have this horizontal asymptote y equals 0. Next, the second graph here is you have a horizontal asymptote at y equals to 3, meaning the degree of the top equals the degree of the bottom, so you get the ratio of their coefficients. And then the third one is the degree of the top is greater than the degree of the bottom by 1. Don't forget this. And that one, there is no horizontal asymptote, and you will have this slant asymptote, which is equal to 3x plus 1. Okay, so these are the example of those graphs. Now, example number 6. For the functions below, identify the horizontal and the slant asymptote using these properties here. So all you have to do is take a look at the degrees of the top and the degree and bottom. So letter A, so the degree of the top is 3, the degree of the bottom is 3. They are the same. So when they are the same, all you have to do is divide, get the coefficients and divide the coefficients. So 6 divided by 2 is equal to 3. So meaning you have a horizontal asymptote at y is equal to 3. So actually this one, y equals 3. Then let's answer first letter C. K of x equals x squared plus 4x over x cubed minus 8. Take a look at the degrees. The degree of the numerator is 2, the degree of the denominator is 3. 2 is less than 3, so meaning you have a horizontal asymptote at y is equal to 0, and that is this, when you have y equals 0. Now how about, that is just an example of this. So y, a horizontal asymptote of y equals 0. Okay, how about letter B? So if we check our degree, the degree of the denominator is 2, the degree of the numerator is 2, the denominator is 1. So that is 2 is greater than 1. So meaning the degree is greater than by 1, because 2 is greater than 1 and it's just greater than by 1. So meaning you have a horizontal asymptote here, And also, one of the reasons for that is when you divide x squared over x is equal to x. And expect that it's going to be a line. So you will have a horizontal and slant asymptote. And how do you get the exact equation of that line? So all you have to do is divide the numerator and the denominator. So remember syntactic division, x plus 2, that's negative 2. The coefficients 1, negative 4, positive 1. Bring down 1, multiply, then add is negative 6. Then negative 4 plus negative 2 is negative 6. Negative 6 times negative 2 is positive 12. If you add this is 13. So you know that this is remainder, constant, and x. So this is x minus 6. So this is your slant asymptote. That is, you have to disregard the remainder. Okay, so again, you have the horizontal asymptote here for letter C, y equals 0. You have the horizontal asymptote for letter A because the degrees are the same. Then you just have to divide their coefficients. 6 divided by 2 is 3. And for letter B, the degree of the numerator is greater than the degree of the denominator just by 1. So you can divide it and expect that it's going to be a line. And that line is going to be a slant asymptote. So when you divide, do not include the remainder. So the equation of your asymptote is x minus 6. Y equals x minus 6. Okay. All right. Now let's answer some lecture questions here. For the following exercise, find the domain of the rational function. So remember, what we do is we have to set the denominator equal to 0. So x squared minus 2x minus 8 is equal to 0. And then this is factorable. Find the factors. X squared, x times x. Find two numbers when you multiply is negative 8. And when you add is negative 2. Yes, that's negative 4 and positive 2. So meaning we have x here, x equals 4 and x equals negative 2. So we can write our domain is going to be from left to right, from negative infinity to negative 2, union from negative 2 to 4, union from 4 to positive infinity. So this is your answer for domain. Okay, 12. For the following exercise, find the domain, the vertical asymptotes, and the horizontal asymptotes of the given function. So number 12, f of x equal to x over x squared minus 9. So just like what we did for the previous problem, set the denominator equal to 0. That's the first step. X squared minus 9 is equal to 0. X squared minus 9 is factorable, so x plus 3, x minus 3 is equal to 0. So you have x equals negative 3 and x is equal to 3 when you set each factor to 0. So meaning from here you can write your domain. So the domain is, where do I write domain? That is, yes, from left to right, negative infinity to negative 3, union from negative 3 to 3, union from 3 to positive infinity. So that is the domain. Next, how do we get the vertical asymptotes? So there are two vertical asymptotes, and remember, if that is the vertical asymptote is your denominator. We did not cancel x plus 3 and x minus 3. Those are the factors of the denominator. So those restrictions are going to be your vertical asymptotes. So x is equal to negative 3 and x is equal to positive 3. Now, do we have a horizontal asymptote? So take a look at the degrees of the numerator and the denominator. The degree of the numerator is 1, the degree of the denominator is 2, and 1 is less than 2. When the degree of the numerator is less than the degree of the denominator, then you have y equals 0 as automatic, that your horizontal asymptote is y equals 0. Okay. Next one. For the following exercise, graph the function and describe the local behavior, meaning the vertical asymptotes, and the end behavior, meaning the horizontal asymptotes, using the arrow notation. Okay, so 28, f of x, x squared minus 4x plus 3 over x squared minus 4x minus 5. So how do we graph this? So please use your graphing calculator or Desmos. I want you to do that now. And then type this as is, x squared minus 4x plus 3 and x squared minus 4x minus 5. When you use Desmos, you will see that you have vertical asymptote at -1 and +5. And the reason why is to find the restrictions, set the denominator equal to 0. So x squared minus 4x minus 5 is factorable, and the factors are x times x. Find two numbers when you multiply is -5, and when you add is -4. That is -5 and +1. So that's why you have, when you set each factor to 0, x is equal to 5 and x is equal to -1. So thus you have these two vertical asymptotes. So since that is your denominator and we did not cancel it from the numerator, so these are your vertical asymptotes. X is equal to 5 and x is equal to -1. So if you look at your graphing calculator, it's gonna look like this, and here, and something like this. Please check it with your graphing calculator. Now, how do we write our arrow notation? So here, let's use with -1, because we have these vertical asymptotes here. So as x approaches 1 from the left, if you follow this graph, this green graph here, it goes up. So f of x approaches positive infinity. And as x approaches 1 from the right, so that is this graph here, it goes down. So f of x approaches negative infinity. Okay. Now, how about when x is equal to 5? So there, because we have two restrictions, so we have to write two arrow notations. So as x approaches 5 from the left, this one, if you follow this, it goes down. So that is f of x approaches to negative infinity. And as x approaches 5 from the right, it goes up. So that is f of x approaches positive infinity. Okay. Do we have horizontal asymptote? So take a look at the degree of the numerator and the denominator. They are the same, so meaning you have to divide their coefficients, get the ratio of the coefficient. So this is 1 and this is 1. 1 divided by 1 is just simply equal to 1. So meaning we can add that as your horizontal asymptote. Sorry, I don't have a space. So since 1 divided by 1 is 1, so horizontal asymptote is y equals 1. So at 1 here, you should have a horizontal asymptote here. So these and these graphs won't touch the horizontal and the vertical asymptotes. Okay, last one. For the following exercise, find the slant asymptote of the function. Slant asymptote because look at the given function f of x equal to x squared plus 5x plus 4 over x plus 1. The degree of the numerator is 2, the degree of the denominator is 1. 2 is greater than 1, it's only greater by 1. So you expect that it's gonna be a line, which is a slant line, and we call it a slant asymptote. Or think about this way, x squared over x is equal to x. So it's gonna be, if it's just x, it's gonna be a line. Okay, but how do we do that? So remember, we use synthetic division. We have to divide the numerator by the denominator. So x minus 1 is 1, and then the coefficients 1, 5, and 4. Bring down 1, multiply, then add 5 plus 1 is 6, 6 times 1 is 6, 4 plus 6 is 10, and remember this remainder constant and x, and we do not use the remainder. So the slant asymptote here is this part, meaning which is y equals x plus 6. Okay, and that's it for this section 3.7. Thank you.